Hi, I'm Yomna.
Hi, I'm Aditya.
Hi, I'm Koushal, and our topic is the laws of thermodynamics. So, the laws of thermodynamics are a group of laws that describe how energy is transferred between objects in the form of heat, and there are four main laws of thermodynamics. But before we can learn about these laws, we have to understand the concept of uh, thermal equilibrium. So, thermal equilibrium is the condition under which two thermodynamic systems come in physical contact with each other, and no heat energy transfer occurs. And these two substances in thermal equilibrium are said to be at the same temperature due to this. So, the first law out of the four laws of thermodynamics is called the Zeroth Law. And it's incredibly important as it allows us to define the concept of a temperature scale. And it basically states that if two systems are in thermal equilibrium with a third system, they then therefore have to be in equilibrium with one another. And this can be demonstrated in a real life application through thermometers. Say, for example, if there were two separate cups of boiling water, and if we place a thermometer into the first cup, it gets warmed by the water until it reads 100 degrees Celsius. We now say that the thermometer is in thermal equilibrium with the first cup of water. And then next, if we were to move that thermometer into the second cup of boiling water and it continues to read 100 degrees Celsius, thermometer is therefore also in thermal equilibrium with the second cup of water. And using the zeroth law of thermodynamics, we can conclude that the two separate cups of boiling water are in thermal equilibrium with each other.
Then we have the first law of thermodynamics, which is better known as the law of conservation of energy. It states that a system's change in internal energy is equivalent to the difference of the net heat transfer into the system and net work done by the system. This is seen in the equation in red. It can also be visualized through the equation K1 plus U1 equals K2 plus U2, in which the initial kinetic energy plus the initial potential energy is equal to the final kinetic energy plus the final potential energy. This is the equation of conservation of energy. The second law states that in all energy exchanges, if no energy enters or leaves a system, the potential energy of the state will always be less than that of the initial state, meaning as energy is transferred or transformed, more and more of it is wasted. This can be seen in the diagram where in an energy transformation, part of the energy will always be unusable afterwards. This unusable energy is called entropy, the amount of energy unavailable to do work. The third law of thermodynamics states that at a temperature of absolute zero, the entropy of a pure crystalline substance, which again is the amount of energy unavailable to do work, must also reach a constant value of zero. Theoretically, at absolute zero, all means of motion would stop, meaning there would be no vibration, rotation, or translational motion. This can be seen in the equation S equals K ln W, where S is entropy, K is Boltzmann's constant, which relates the average kinetic energy of a particle in a gas with the temperature of the gas, and W is the number of microstates, the number of possible arrangements of a molecule's motional energy. When the number of microstates is 1, or there is only one possible arrangement of the motional energy of that molecule left, the entropy is 0, which makes sense because that means the molecule can't move, and we know that there is no motion at absolute 0.
So a modern real-world application of thermodynamics is actually a refrigerator, which generally falls under industry. Refrigerators are open systems which dispel heat from a closed space to a warmer area, thus decreasing the temperature. So the first law of thermodynamics, otherwise known as the law of conservation of energy, basically states that energy cannot be created nor destroyed, only converted. So in a refrigerator, electrical energy is first converted into mechanical energy by a motor. The motor drives a compressor And this compressor then heats the refrigerants. Mechanical energy is converted to thermal energy in this process. So it goes from electrical energy to mechanical energy to thermal energy. Any change in the internal energy of the refrigerator is equal to the heat added from an action such as opening the refrigerator door minus the work done by the refrigerator system through the motor as well as other components. The second law of thermodynamics basically states that heat will always flow spontaneously from hot to cold, but never the other way around. So according to second law, it is not possible for heat to flow from a colder body to a warmer body without any work having been done to accomplish this flow. Energy will not flow spontaneously from a low temperature object to a higher temperature object. So this essentially makes a quote unquote perfect refrigerator impossible. A refrigerator causes heat to flow from cold to hot by inputting work into the equation, which cools the space inside the refrigerator as shown in the image to the right below. Work is this cyclical process works by work is inputted, which compresses a coolant, increasing the temperature above the room's temperature. Heat then flows from this coolant to the air in the room, reducing the temperature of the coolant itself. Then the coolant expands and it cools down below the temperature of the refrigerator. And from there, the heat flows from the refrigerator to the coolant, decreasing the temperature inside. So the third law of thermodynamics, as stated earlier, is that at a temperature of absolute zero, entropy will also approach zero, causing the refrigeration techniques to fail. And so basically, this is because the refrigeration is a cyclical process, again, as stated earlier, that requires the continuation expelling of heats. So to maintain a constant low temperature, one connects a heat sink to the system to bring heat out of the system. Heat leaving the system indicates that the entropy is actually decreasing. So in a common home refrigerator, the parameter usually used is volume. So when you compress refrigerant in its gas phase, it becomes a liquid to which heat is expelled. This refrigerant fluid is then deposited into the radiator. So as the temperature decreases, the internal energy decreases as well. So here we have our information citations. So all of our material used and presented in the slideshow has come from these sources. As well as our photo citations. Thank you.
Thank you.
Thank you very much for listening.